So to start off, can I see show of hands who had trial A? A. Wonderful. All right, my trial A's. Hey, what did your graph look like? Natalie. All right, so I see trial A. Looks like a straight line. Got time on the x-axis, position on the y-axis. Is a straight line. What was the y-intercept you got in your equation for that? Julia? You got to vote for 0. What was the y-intercept you got for yours? You got 0. How about from back table? 0. 0. Slope of this line, positive, negative, or 0? Positive. Okay, so I'm going to put my linear graph. This is an object that started at the origin and moves forward. Cool. What about person B? Who is the person B's out there? So what did your graph look like for this one? All right, name. Leah. All right, straight line again. Straight line again, but what's different about your line than person A's?
Ours started at 50.
Starts at 50. Leah, where did yours start? 50. How about Nathan? Were you the person B? Oh, Will, what did you get? Negative 50. So like down here. All right. So what did you get? Yeah. Negative 50. And then how about 50? I think the negative 50s might just be your graph if your graph is upside down. Oh, okay. I could see that. I'm gonna keep it as positive 50 just so like we have them straight on the board because otherwise it's kind of difficult to draw both graphs. Slope. Was your slope positive, negative, or 0? Positive. So I've still got a straight line with a positive slope. But the difference for my motion is instead of starting at the origin, B started at 50 centimeters in front of the origin. Now, let's say you do your equation and your equation says like 44 instead of 50. That might just be that with the uncertainty in each individual data point, that it's giving you a little bit of error. No big deal. So as a general rule, what your y-intercept of your graph indicates is your starting position. In A, this started at the origin, so your starting position is at 0. But in B, the car started in front of the origin, so your y-intercept is at 50. So PT for point, starting point.
Can I ask why distance isn't x?
Oh, distance is x because in the, you know how you have it set up horizontal? Huh?
Why it's not?
Why it's not distance is x?
Why is the distance your x?
Like, why isn't it not on your
Yeah.
x-axis? Oh, okay. So we normally put time on the x-axis because it makes the slope easier. So technically, I could switch position and time, but I keep the time on the x-axis because it's easier for the thing that comes next. Right? And they do depend on each other, right? Like as time goes, the position also changes. So you could say that the time passing is what allows the position to change. So time would be your independent variable and position dependent. Both ways. All right, but then person C comes along, and who are my people C? All right, person C, what does your graph look like? Samantha.
Starts at 150 and it's a negative graph.
All right, now it starts higher up even. It's a negative graph that goes down. So for C, this is an object that starts in front of the origin, right? It still starts at positive 150. But now it's going backwards. The going backwards has changed the motion somehow, and it has changed the graph. What's the difference between forward and backward motion on a graph that looks like this? All my graphs that are going forward have a specific type of slope. What do my forward motion graphs have for their slope?
Positive.
Positive. So the forward bit gives you this positive slope. All right. That backward bit, if you have an object that's moving back towards the origin, that's going to have a negative slope. So the direction of my line tells me whether you're moving forward or backward. And you can think of this as like, if I start at 150, the position gets smaller and smaller and smaller. It's getting closer and closer and closer to the origin as it travels, making the position decrease. So I'm going to group A, B, and C into a category. We'll see if this makes sense. A, B, and C all represent constant velocity motion. These are objects that are going with the same speed the whole time and in the same direction. They don't turn around. These objects are in dynamic equilibrium. So the force that goes forward, the applied force, is equal to the friction that pulls backwards, or drag. This is dynamic equilibrium. But then I get to person D, and person D had the fan cart. Who are my person D fan carts? So what did your graph look like?
It was positive and then curved
Positive and curved up. Okay. What was your y-intercept on that one?
up.
20? Meredith, what was your y-intercept? 20? 20. All right. So this is an object that starts in front of the origin. So the y-intercept still is going to make sense. It starts in front of the origin, started at 20. But it has a curve that goes upwards, a parabola. Right? This type of motion is accelerated motion. And if it's accelerating, it's not traveling at constant velocity. This is not in equilibrium. There is more force to the right than there is to the left. That might be something like the applied force from the fan going forward is more than the drag holding it back. So how I can tell on this graph what type of acceleration it is, it's going to be based on the shape or curvature. And I'm going to draw some pictures in here that will help. Right? So under accelerating, I'm going to draw some extra graphs. I'm actually going to rearrange this for 1 second. There's 4 types of accelerating shapes. So it could be curved up, curved down, going backward, or forward. Any sort of curved graph indicates that your object is accelerating, that it's not in equilibrium. It's either speeding up or slowing down. I can still use the backwards and forwards rule where like this one is going backwards because the position is decreasing. Whereas this one is going forwards because the position is increasing. But the curvature, the shape of this graph tells you whether it's positive or negative acceleration. So I have a rule to help us here. The top 2 graphs have curves that are upward facing. You gotta make part of a smiley face. Now, smiles I generally associate with like positive. That's positive acceleration. Both of these are examples of objects that are positively accelerating. And to me, I'm like, all right, curvature upward, positive acceleration. If you were in math class, that would be like A in that parabola equation is positive. Right? My downward facing curves indicate negative acceleration. They're objects that have acceleration that is in the negative direction. So maybe friction takes over from applied force. Right? So I said there's a limited number of graphs. There is one more equilibrium state, but I didn't have anyone do it because it is painfully uninteresting. What is the third equilibrium state? There's something dynamic and not an equilibrium, Timothy?
When it's not moving at all.
All right, and when it's not moving at all, it's kind of boring. So I'm going to show you my picture for that to help you imagine this not moving state. All right. To imagine the not moving state, I'm going to have us picture this motion detector with a cup of coffee. All right. Now, this green device I have here is a motion detector. And when we do this in the next unit, what the motion detector does is essentially like, it's essentially sonar. It puts out little bits of sound, bounces them off the coffee cup, and takes how much time it takes to get back. So this coffee cup, as it's just sitting there, sound bounces off that front edge of the coffee cup. The coffee cup is not moving. So in the first second of motion, it's reading it at 4 meters away. In the next second of motion, it's still 4 meters away. On the second and third and fourth, it's still at 4 meters away. I didn't have any of us do this particular trial because it would be like incredibly uninteresting. If you get a graph that's a horizontal line, that indicates that your object is not moving at all. And it's in the third state, static equilibrium. Right? So let's put that in our last picture. I kind of put it in this back corner over here. Right. So the last one would be static equilibrium. The net force is still 0, but that means your object isn't going anywhere. And your position versus time graph would be some sort of horizontal line. The line tells you it's at 4 meters the whole time, and it doesn't change. So a horizontal line tells you that this is an object at rest. So those are all of the graphs. We have static equilibrium, that's horizontal. Dynamic is going to be a linear graph, nice straight line, moving forward or backward with the intercept that we can read. And last one over in the corner are accelerating, not an equilibrium, where we can figure out if it's going forward or backward, and the direction of acceleration, positive or negative, based on the shape as well. So I'm going to have us try this. I'm going to have us try this in a matching game. So matching game for right now is going to be on Nearpod. So if you go to join.nearpod.com, you can use your notes for this. You can use these pictures for this. People always ask if you can take pictures of the board. You can always take pictures of the board. As long as I don't do something like erase it before you do it, you can always take pictures of the board. So you're going to join.nearpod.com. Code's going to come up in a second. And when you get there, we're going to see if we can figure out